Let's take a look at density. Now, there are a number of symbols that are used in various textbooks. The symbol that is most commonly used for density is the Greek letter rho, spelled R-H-O, and it looks kind of like a P, but that is the symbol that I will be using for density. And the definition of density is mass divided by volume. So from a conceptual point of view, if I've got something that is incredibly massive, and we would generally know that by the fact that it's heavy, but that doesn't necessarily have to be heavy in order to have a lot of mass. For example, an object on the moon might not be heavy even though it has a lot of mass, but on Earth it would be heavy because mass and weight are different. But it is the amount of mass in the volume, so if I have something that is very massive in a small amount of space, it is considered to be very dense, but if I take that same mass and spread it out, it is less dense. Now the units, the SI units of density, are the SI units of mass over the SI units of volume, which would be kilograms per cubic meter. However, because the international standard has not been around forever, before the standard was grams and centimeters, and so otherwise known as the CGS system, and so you'll often find a lot of grams per cubic centimeter in various textbooks and websites. Now, just as a side note, there's also something known as surface density, which is mass over area, and the symbol I typically use is the lowercase sigma, although the eta is also used in some textbooks. And then linear density, mu, is mass over length, and sometimes a lambda is used for linear density, but I tend to use the mu. Now, because water, H2O, is a rather common substance throughout the world, that was considered to be the standard for easy dissemination of information throughout the world, so that was established as 1 gram per cubic centimeter. And at this point, we've narrowed it down to at 4 degrees Celsius, it's 1 gram per cubic centimeter. And just to give you an idea of the range of it, at 0 degrees Celsius, it is less dense, so 1.0002 grams per cubic centimeter. And then at boiling point, 1.06 grams per cubic centimeter. These are the densities of liquid water, by the way. And then a conversion, because often grams per cubic centimeter is used to figure out how many kilograms per cubic meter it is. We just do a conversion down here, converting first grams to kilograms, and then centimeters to meters, and we are cubing it because we have 3 centimeters we need to convert, and so 1,000 kilograms per cubic meter is 1 gram per cubic centimeter. So density of water, 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. So for example, I weigh about 215 pounds, slightly less as of last week. And so converting that, first I need to convert it into newtons. So that is the conversion factor. We can go more decimal places if needed, but that's where I went. My weight is 956.32 newtons. Now I know weight is equal to mass times acceleration due to gravity. And so mass is weight divided by the acceleration due to gravity. Just divide both sides by g. And I'm in Winston-Salem, and that is the acceleration due to gravity in Winston-Salem, at least where I am right now. And so weight divided by that, and I have a mass of 97.604 kilograms. Now I can somewhat float in water. I know that if I take a deep breath, I will stay afloat, at least part of me will. I'll stay at the surface of the water. If I exhale, I will sink to the bottom. So my density is about that of water. And so I'm going to make that assumption. My density is about that of water. So in terms of kilograms per cubic meter. And so my density, which is about 1,000 kilograms cubic meter, is equal to my mass divided by my volume. You go through the math. Basically, I'm doing a little cross multiplication here, and I end up with 97.604 divided by 1,000. And just note, I can always turn anything into a fraction here by just sticking it over 1. And so when dealing with two fractions equal to each other, solving for an unknown, you multiply the diagonal you know and divide by what's left over, and that gets you your unknown. And so that is my volume, just shy of 1/10 of a cubic meter. So I was then curious of, could I confirm that through other measurements? And so let's see if I can figure out what my volume is by part. And so this is basically a sketch of me, not really to scale because my arms aren't that short, but I estimated my head to be a sphere, my neck to be a cylinder, my arms to be cylinders, my hands balled up. See that my volume of my hand is pretty much the same like that as like that. So my hands I treated as spheres, my torso as an elliptical cylinder. So imagine a cylinder and just squish it some. My midsection also elliptical cylinder. My legs, cylinders, my foot, rectangular solid. So these are the sort of the crude approximations I'm doing. These are the ones for which I have a formula. I then went through and I started doing measurements. For example, my head, I measured the circumference. I actually measured it 3 different ways, and those are the values in centimeters. And so came out with an average circumference of 64.6 repeating centimeters. From that, I found the radius, because the circumference is equal to 2 pi times the radius. And once I have the radius, I plug into the volume of a sphere. And I came out with that as the volume of my head. I have only one of them. I'm doing a running tally of my volume on the side over here. My neck was a cylinder, and there's the formula for a cylinder. I measured the circumference around 3 different times. I measured the length 3 different times, basically 3 different points on my neck. For example, I measured that distance, and that distance. And I came out with a length of 12.76 repeating centimeters and a circumference of 38.3 repeating centimeters. From that, I figured out my radius, plugged into my formula, came out with that as the volume of my neck. And then so on. And I'll just sort of move this so that you can see. And again, for each of them, I did 3 measurements, although I think I did more than 3 for one of them. For each of them, there was a formula. For instance, the arm was a cylinder. There's the formula. These are the 2 measurements I made. Did that calculation, plugged into the formula, and I continued that pattern on for the rest of it. Came out with the volume for each of them, and then multiplied by the number of them I have. For example, this is my arm. I have 2 arms, and so that's the volume for one arm times 2. Added it to my running volume, my running tally. And it eventually end up with a volume in cubic meters of 0.097526 cubic meters. Comparing that to what I had by assuming I had the density of water, I came out with 0.0976. And so I'm pretty darn close. It starts to deviate once you get into the 10,000th of a cubic meter. So my assumption that my density is about that of water seems valid. And the next bit goes back to a post that my brother made on Facebook when Hurricane Floyd was off the coast of North Carolina in September of 1999. He made a comment on Facebook that they're getting hit by a ton of rain, and I began to wonder, what is the volume of a ton of rain? And so I did first converted tons into newtons. Ton is 2,000 pounds, 4.448 newtons per pound, and I ended up with the weight of it. Used a generic 9.8 meters per second squared because it's not Winston-Salem, and that's probably good enough for the coast of North Carolina, and ended up with 907.755 kilograms. Density of rain, we assume that rain is close enough to there wasn't a huge range in the density of water, but we end up with that volume right there, which is about 3 bathtubs full. So I then replied to my brother by saying, a ton of rain. That's about 3 bathtubs full. I guess you're saying they're getting a light mist. And I know he did not mean that literally. I hope he did not mean that literally, because he was way off.